So now we're going to talk about logarithms. Simply put, logarithms are the inverse of exponential equations. So please bear in mind that the output of an exponential equation is some value that comes, remember a and b are constants, right? And we're just going to stick to really simple exponential equations, right? B to the x. So what happens is we take x, which is an exponent, and we put it in our function. This is what exponential function is doing, right? Taking an x, which is an exponent, and we're yielding y, which is a value. And then this would be an exponential function. And then a log function should take this y value. I love drawing function machines. I don't know if you've noticed this. And what it should churn out is, so this is a logarithmic function. A logarithmic function takes a value and churns out, well, the original x. Now this is nothing new because this is just functions and its inverses. So if this was f of x, this would be the inverse. We've seen this before, right? But remember, x is an exponent. So oftentimes we will say that logarithms or logs are exponents. So when you're taking the logarithm, which is a way to undo something that was an exponent, right? Then we're talking about this log being the exponent. So what's happening is x, which is our exponent, is equaling something to do with y, and we call that taking the log of that. Now, log, short for logarithm. I should probably point out that x and x match in this case, and it's very good we keep it that way. They're both the exponents. Y is the input value, right? So we're taking the log of it. Now, this is the case, it is the case that for any given exponential equation that has some base, right, that there's going to be a corresponding logarithm with the same base. So we'd say that x, which is the exponent, is the log base b of y. So this is the log base b of y. That's how that would be read, okay? So log base b of y. And that is basically what a logarithm is. So here's some gyrations to show you about this. Exponential form to logarithm form and vice versa. So remember, y equals b to the x, the corresponding inverse, right, if that's the original function, is x would equal the log base b of y. So for instance, what if I had 3 to the x equals 9? That would be an exponential equation, so we call that exponential form. What would the corresponding logarithmic form be? Well, it would be, well, x would be the exponent. And what is the base of this exponential? Well, it is base 3, so it would be a log base 3 of, well, what's our output value? Y, right? This corresponds to the y. So that's our input value into this, right? Now this actually is a question we can answer, because if you're looking at this logarithmic equation, log base 3 of 9 is a question. 3 to what power equals 9? Well, it's pretty obvious that it's got to be 3 squared. I know some of you are going to say 3 because 3 times 3 is 9, but it's actually 3 squared, 3 times 3. So that would mean that this is equal to 2. Let's try a couple more. Like, what if I had 1/4 to the second equals y? Well, is this an exponential equation? Yes. Do we know the exponent? Yes. That would be the 2. 2 is the exponent, right? Equals the log, what's the base of the exponential? Well, 1/4, so that would be that, right? And then what would that be? Log base b of, what's our output here? Y, right? Now in this case, we wouldn't actually need logs for this, but we know that that has to be 1/16 because 1/4 squared is. But for the purposes of rewriting in what is called log form, that is what we would do. In general, when we're talking y equals b to the x, you're talking about this x is going to be the exponent. So you can kind of think of this as doing a little circle thing kind of thing. I've seen that before, but I'm not a big fan of it. X is going to equal, it's always going to be tied together through the base. So the base of the exponential, base of the log must be the same, okay, of y. Now, I should probably mention at this point that when we're talking about the base of the exponential corresponding to the base of the log, now remember these are inverse functions of each other, right? So we would write that as, let's say that f of x was equal to 2 to the x. That would mean the f inverse of x, now this is where you need to make sure that we don't stay confused here, would be log base 2 of x. Please bear in mind that this x here is not an x, it's actually f of x, or the output, and that this f inverse of x is not a y value, it's really the x, or the exponent, okay? Remember, we just exchanged what these were, okay? Let's take a look. What else we got? Graphs of logarithmic functions. So let's take a look at something simple like 10 to the x. 10 to the x would be, we'll multiply by 10 each time, but the y-intercept would be 1, so it would look something like this. What would the corresponding log function be? Well, it'd be x equals log, base of the exponent is 10, so base 10 of y. Now, realistically, if we wanted to graph this, we would probably re-express it in terms of y and x. So we would say y equals log base 10 of x, okay? We know, however, though, that because that these are inverses of each other, they're just reflections over this line here, which that's the line y equals x, as we know, right? So the reflections over the lines y equals x. So graphically, when we're looking at a log, it looks kind of like an exponential. Looks like that. Now, exponentials have this horizontal asymptote at 0, whereas logarithmic functions have a vertical asymptote at 0. So vertical asymptote at x equals 0. This point is 0, 1, right? So technically this point here is 0, 1, which makes this point 1, 0, right? Typically, if you take a look at this, now if we think about this carefully, if we were trying to figure out what if the, so this would be 1, 0, x would be the exponent, right? 10 to what power is equal, so 10 to the 0th power is equal to 1, right? So that would mean that we plug in 0, we get 1. Here, the log base 10 of, well, that would be 1 would equal the log base 10 of, that would be 0, right? Now, this does mean that if we're looking at the log base 10 of 1, that would mean that we're looking at 10 to what power? So that would mean the exponent would have to be that, right? Because 10 to the 0 equals 1. That's how tying those together in your mind can make this a lot easier. But in general, they're reflections. Now, I should probably mention this. A log base 10 is often referred to as the common log. The reason we say that is because we have a base 10 number system, you know, numbers 1 through 9, or 0 through 9 actually. So that would mean, that's just written as log, okay? So let's just reinforce that. The common log is a log base 10, and it's just written as log. So if I were to say log of 5, so y equals log of 5, I would assume that, because you didn't write the base, that that's a log base 10 of 5, which would mean 10 to y. Remember, log is an exponent, equals an exponent. 10 to the y equals 5, right? Would be the corresponding exponential form. Oh heck, let's go there. There's also something called a natural log. Natural log, which is just a log base e. E being the number that we talked about for continuous change. So when we're looking at those, all those continuous change functions, there's a log base for that, and that is written as ln, log natural. So if I say y equals ln x, I'm saying that y is equal to the log base e of x, which means that the corresponding inverse function, right, if this is f of x, right, the corresponding inverse function would be, well, it'd be e to the y equals x. So the inverse function would be e to the x. Okay. All right. And that is a crash course in logs and how they're related to exponentials. They are inverses. Okay.